So this is the recording for 9.5. It does start off with a warm-up, and then we're going to get into finding arc measures is what 9.5 is about. So for the warm-up, we'll do number 1 together just to talk about tangent, just to clarify a little bit more from yesterday. But for number 2, this is just, there's a lot of algebra that goes with this, so we'll kind of, and there's not tons of room, unfortunately, either. So if you want to try this one out, you can. There's a lot of decimals and fractions that you can kind of work with here, but we can go over that at a later time, too. So number 1 just says, write an equation of a circle that's both tangent to the x and the y-axis. So there's many answers possible here. That's why your answer could be different from mine. If you want to take a minute and just kind of write your own, that would work too, but I'll go ahead and draw a sketch of like what this kind of means. So you want to draw your circle so that it hits one time on the x-axis and one time on the y-axis. So here's the x-axis and here's the y-axis, one spot each. You could have done it on the negative or the positive, doesn't matter which part of it you do. I'm just keeping mine in the first quadrant. So like imagine a circle like this, where again it only can hit one time here and one time here. So now as we pick the numbers, you first probably want to pick your radius before you decide where your center is going to be. So like I want to make my radius 3. So far I know I have to do something in parentheses squared, something in parentheses squared. Now this would be 9 because I know that when I put it in my equation, r squared is 9. Okay, so now to figure out the beginning part, I need to tell my graph to get to the center by going 3 away because of the radius there, so that it can touch the x and the y-axis, right? So I need this to be at 3, and I'm going to move it to the right 3, and I also need it to be at the height of 3, or like up 3. So that's why I did x minus 3 squared and y minus 3 squared. But as long as you pick whatever radius, and then you pick these numbers as this, whatever your radius is before you squared it, that should make it so that it sits right on touching just x and y once. Okay, so that's one possible answer. It does not have to be the exact same as yours, but that's the idea. Okay, so now we're going to move into arc measures. So on arc measure, we're working with circles. We keep kind of drawing segments like radius and diameters into our diagrams of circles, and as we're doing that, we're kind of like dividing up the circle. And so by doing that, it kind of like makes these sections, which will be called arcs. So the first thing we have is a lot more vocabulary, so please make sure you're kind of reviewing all of this. We have central angle, which is an angle whose vertex is at the center of the circle. I'll show you where that is. There's a minor arc, which is the part of a circle that's less than halfway around the circle. So imagine halfway around the circle is going to be 180 degrees, or think of like a semicircle, but less than that would mean anything less than 180. So it could be 90 degrees, it could be 70 degrees, it could be 10 degrees. Those are all different types of minor arcs. Major arcs are the opposite of that, so that would be the part of the circle that's more than halfway around the circle. So degrees that are more than 180, because 180 is, again, semicircle. So that's the last word here. A semicircle is an arc with endpoints that are the endpoints of a diameter, because the diameter has to go to like split the circle into 2 equal halves, and that's exactly when a semicircle is created. So let's kind of identify from this diagram a little bit about each of these vocabulary words. So here's what we know so far. This circle, the center is D, right? Point D right here. And AC, we already know, segment AC is the diameter, just looking at the diagram, because A to C is a chord that passes through the center. And BD is a radius, in case I wanted to know that piece as well. Okay, it's just a little bit more detail that's true about this diagram. Okay, so now let's figure out, what about these new vocabulary words? Where are all the things there? So a central angle is an angle whose vertex is at the center of the circle. Well, since angle D, or point D, is the center, any angle that's using point D as its vertex just means like the point where the angle is being measured from, that would be a central angle. So we have angle BDC, you have angle ADB, Technically, we even have angle AC, or I'm sorry, ABC because, or not ABC, ADC, because it is like a straight line. Those were called straight angles before. We don't really mention those as angles as much though, so I'm not going to bother writing it. Remember that with these ones, you can change the order of the letters. Like you could say CDB, or you could say BDA, but you can't change like where D is. D has to be in the middle of each of those because that's what is using the vertex. Okay, so those are examples of central angles because they're using the vertex at the center. And we're going to see a different type of angle next week that is not central, and so we'll see what happens there. A minor arc, we said, was any number that's less than, it's a degree that is less than 180 because it's got to be smaller than a semicircle. So like if I see the semicircle, it's all of this part. Well, an arc, here's how arcs are written. They use two letters to create that arc. So for example, B to C is, you can clearly tell that this measurement here is less than 180 degrees because the whole thing here is 180. That leaves me with 180 to work with. So one minor arc could be BC, and we draw a little like McDonald's arc, like just like that little arc on top of it to show that this is an arc. It's not a line. It's not any other type of geometric, shape or figure. It is an arc. So you're trying to talk about arc BC as a minor arc. Another example could be arc AB. That's also considered a minor arc because it's less than 180 degrees. Whereas a major arc has to be more than 180 degrees. Now, so far we've seen two letters that created these arcs. You can even do three letters, depending on how you're trying to say go from here to here. So like if I want to go from A to B, usually we take the closest way to get to from A to B. So when I say arc AB, it's referring to this amount right here, which is a minor arc. But if I want it to be a major arc, I want it to go all the way around this way, then I would have to tell it to go from A to C to B. You're kind of going in order of the letters, following along until you hit the next one. So it has to go in the same order, A to C and then B. Whereas if I did ABC, ABC would just be a semicircle because I'm only going halfway around the circle. So make sure the order of the letters matters. What if I didn't want to start at A? I could have done BCA. That would be fine as a major arc because, again, it would be more than 180 degrees. I could do CAB. That would be fine too. It's, again, more than 180. So if you want to write more examples for yourself, feel free to do that. I'll just write etc. because there can be lots of examples possible on these. And finally, a semicircle, you can either just use two letters again that says from A to C, that's going to form a semicircle because it's actually equal to 180 degrees. Right? It's not more than or less than 180. It is actually 180. And so that's how we work with the diagram. That's what you're going to be doing as we work with arcs. We're going to start measuring the arcs, though, coming up on the next part here. And so sometimes a measurement will be given to you, and then you'll have to kind of work with that. Well, there's one more piece of info that is very important right here. It says the measure of an arc is equal to the measure of its central angle. So what we just saw above was this name called a central angle, and I'm highlighting this because it's really that important. Anytime you see a central angle and you're being asked to find the arc measure that opens up to that same central angle. So like let's say this angle right over here was given to me as like 30 degrees. Then this arc that follows with that same angle is going to also be the exact same angle. So if this is 30, that's 30. So if you look at this diagram coming up here, we're about to kind of find the different angle measures. It shows me here that if I have arc ED, the measure of arc ED, if you look at my diagram here, this is E to D, that would have to equal the same as this angle that opens up to arc ED. So that could be angle ECD, which we know in this diagram here is 117 degrees is ECD, so this would have to be 117 degrees as well. So angle measures are measured on the inside part of the circle. Arc measures are measured on like the actual circle circumference. Like it's telling you what, if you were to measure from here to here, what portion of the circle is it? We know the whole thing is 360 degrees. So this little part here it's saying is 117 of it. We know halfway is 180 degrees. So that's like, again, deciding how much of it do we have. So we're going to kind of work with this diagram here to answer the following questions. Anytime you see the little arc symbol on top, it's talking about finding the outside part, not the angle part. But those two correspond. So if you know one, you know the other one. So for example, on this next one, if I wanted to kind of find all the missing pieces, I know that this right here has to be 180 degrees because it's a semicircle from D to F. And E to F, I can just do either 180 minus 117, and I find out that this is 63 degrees. That means that this angle is also 63 degrees. You can mark on both as equaling 63 degrees. Okay, so also another way to check it is that this is a linear pair. Those two angles are supplementary. They have to add up to 180, and that's exactly what happens. Okay, so 63 degrees there. Now that we've kind of labeled a lot of it, let's go through and answer these questions. The first one says, can you find the measure of arc DEF? Just find letter D, go in the same order. D to E to F creates a semicircle, right? It goes right here around, and so that would just be either 117 plus 63, or you can already tell that it's a semicircle because it's halfway. It's with this diameter. The diameter always has to be part of the semicircle. Okay, so that's 180. And we also, I'm going to label what type of vocab word goes with it, like from above. So like this one is semicircle because it's equal to 180. If it's a major arc, I'll write major arc. If it's a minor, then we'll write minor. Okay, so the next one just says E to F. That's from here to here. Just that little portion is 63 degrees. And that means it's a minor arc because it's less than 180. And finally, for the last one, we want to go from E to F to D. So you have to add together from E to F, which is 63. So I'll do it here. And another 180 degrees from F to D. So 180 plus 63, it comes out to 243. That is the answer here. Whoops. Okay, so 243 would be the arc measure from E to F to D. It also, another way you could figure that out would be to do 360 minus 117, and you would also find out what that whole part was. Because altogether, all of the angles have to add up to 360. Otherwise, something went wrong. Okay, so that's a major arc on letter C. Okay, so we did a semicircle, a minor arc, and a major arc. And then we have just a conclusion on the next page, and then we're going to just kind of do a few more examples like this. Okay, so if we go to the next page here, here's our summary or conclusion. It says the measure of a minor arc is always greater than 0 degrees and less than 180 degrees. Okay, then we have the measure of a semicircle is always equal to 180 degrees. And finally, the measure of a major arc is always greater than 180 degrees and less than 360 degrees. Okay, so that's how you can kind of memorize each one of those. Okay, and now we're on to our first example here. These do go fairly quick because you're just literally looking at the diagram, the circles, to help you figure out what's missing. It says you join a new bank and divide your money several ways, as shown in the circled graph at the right. Find the indicated arc measures. So from B to D, and it shows you the angle measures for the central angles. Remember, that's the same as the arc measures. So it's like from B to D, you have to ask yourself, well, which way am I going? B to D this way, B to D this way, and it's usually measured with the smallest, like the quickest way to get there. B to D this way is going to be quicker than going the other way, right? 55 degrees here and 105. So if I add up 55 and 105, I get 160 degrees. So That would be the measure of arc BD. And then we have measure of arc BCD. So this one clearly tells us I want to go from B to C to D. That means you follow the order. 140 plus 60 is 200 degrees. Then we have BCA, B to C all the way to A here. And again, you have to follow the order even though it is a longer like round. Instead of just going B to A, it wants to go in this entire order. So B to C was 140, C to D was 60, D to A is 105. You either have to add up all three of these numbers together, or you could do 360 minus just this leftover one, 55, and that would give you the whole angle, because it's the whole arc measure, because everything else from here all the way across until you're just leaving out 55 degrees. So I feel like that's quicker. 360 minus 55 is 305 degrees. Don't forget the degree symbols every time you write your answer, but that's all we're doing on that first example. Then parts D and E kind of take it one step further and say, well, if you've invested some money, specifically it says $5,000 into what percentage is invested in a money market account. So right here it says 140 degrees. You just have to take that degrees and divide by 360 to figure out what percent is it, how much of it is, because that's how circle graphs work here. And so this one comes out to 0.3888, I would say, if you round to like that many numbers after. You really just need to decide how to round. So as a percentage, you have to move the decimal point 2 spots to the right. So this would be, or you like multiply by 100 essentially. So this would be about 39% if you round that 38.88 up. And same thing for the second one. It says if you invested $2,400 total, how much money is there if you combine your checking and savings accounts? So these two checking and savings together are 105 plus 55, which would be 160. Now this time it's talking about how much money. It's not just saying the percentage. Here, when we were just working with percentage, the money that we invested didn't even matter. But here I have to kind of make a proportion to say, like, I'm still doing 160 over 360, but if I have a total of $2,400, I want to know how much money is that percent going to be. Okay, so that's the proportion you're solving. Or you could figure out what percent this is and then take that of $2,400, and it comes out to $1,066.67 if you round to the nearest hundred, or like cent basically. Or you could just round to like the nearest dollar and it'd be $1,067. It didn't really say how to round, so you can pick. All right, so that's kind of the idea with working with arc measures. We are finishing up with a few other concepts with arcs, which is like working with the word congruence. Like, what does it mean for arcs to be congruent to one another, just like we've done it with angles before. So congruent arcs, and this is just another vocab word we can use. What does it mean for two geometric figures to be congruent? We know that if they're figures and they're congruent, it says use one word to answer the question. The one word I would think of is same. Those two figures have to be exactly the same. Same angles, same everything, right? So they just are exactly the same. But what must be true about two arcs for them to be congruent? This will tell us a little more detail. So congruent arcs have the same arc measures and are on the same circle. And are on the same circle, or can also be on a congruent circle. So if I'm looking at like two circles that have been told to me that are congruent to each other, so if it says like circle A and circle B are congruent, and then you notice that the arc, they both have like 30-degree arcs, then you would be able to say that those are congruent arcs. So there's two criteria you're looking for. You can't just say that two arcs are congruent if they have the same measure but they're not on the same circle, or they're not congruent circles. So look for radius to be the same in order to show that something is the same circle. Okay? So congruent, we're going to look at congruent circles and congruent arcs. So congruent arcs, I'll write down here that two arcs are congruent if they have the same measure and arcs have to be on the same or congruent circles. So I know that's kind of repeating it again, just to have it kind of clearly understood that that's what a congruent arc is. Whereas congruent circles, our two circles are congruent if they have the same radius. Okay, so let's kind of have some examples to make sure we understand this. And we'll kind of practice them down here as well. If they have the same radius, that means like I could have a circle with whatever. It doesn't have to be drawn one on top of the other, but you know these are not perfect looking. But let's say this radius was 7 and this one was 7 too. Then sure, those are an example of radius that are the same, and therefore the circles are congruent. Whereas congruent arcs, I would need to show that they're first of all on the same circle. Or they're having the same exact radius in order. Like this would be a non-example if you want to write an example for yourself. Let's say I have one circle that has a radius of 7 and it creates this arc measure that's like 80 degrees. And this other circle that has a radius of 9, but it still creates that same 80 degrees. These two circles, even though they have the same arc measure, their arc measures are not congruent because the circles themselves are not congruent because the radiuses are not the same, right? So this would be a non-example, not congruent arcs. Okay, so let's kind of figure that out on the bottom because there's some examples there. It says, tell whether the given arcs are congruent and explain why or why not. So the first one shows you that we're trying to decide are arc BC and DE the same, or are they congruent? And the answer here would be yes. They both sit in the same circle that has the exact same radius, so that the circles themselves are congruent, and the measure of arc BC is equal to the measure of arc DE, which is 75 degrees for both of them. So then I'll also say, and BC, arc BC and arc DE are on the same circle. And then for part B, we have same thing, but look carefully at this. There's actually two circles on this one. There's a smaller circle here, and it's labeled with this to this. Point is A. And then there's a bigger circle that's labeled that this arc here is C to D, right? So C to D and A to B. This one is actually no. Even though they both have the exact same arc measure, they are not congruent arcs. So although arc CD is equal to arc AB, measure of arc AB, which all equals 80 degrees, the arcs are not in the same or congruent circles because the radii are not the same, or radius, whatever way you want to say it. All right, and we finish up with one final one. It shows us the 90-degree angle there. That means the arc measure is also 90 degrees. And the tick mark here that shows you that the radius is the same for both. So yes, this would be an example where the circles are congruent because the radius were congruent. So circles are congruent since radii were congruent. And the measure of arc GF or FG is equal to the measure of arc HJ, and that equals 90 degrees. All right, and we are done here. So I know that was a little bit longer. Tomorrow we will, or I'm sorry, on Monday we will finish up reviewing, kind of working with your review packet, and also the review that's on the next page of this packet. All right, if you do have questions, bring them on Monday.